Okay, so we got the eigenvalue and the corresponding eigenvector. So 1, 2 is the eigenvector corresponding to 5, and 1, -1 was an eigenvector corresponding to lambda equals to -1. And now let's see how you can make this as a solution to the differential equation. So you're going to do the following. You say u1t as you take the eigenvector and multiply it to e to the eigenvalue times t. And I claim that that's a solution. The same thing with this. I can make u2t as eigenvalue times e to the negative t. It's -1 times t. Okay. And I claim that's a solution to the original differential equation. Now let's see why. Well, first, what was the definition of the eigenvector? It was that if you have 1, 2, 4, 3 times 1, 2 would equal to 5 times 1, 2. This is the definition of an eigenvector with eigenvalue 5, right? You can actually show that this is true by doing direct computation. 1 times 1, 2 times 2, add them up, you get 5. 5 times 1, that's 5. So the top row is equal, right? How about this one? 4 times 1 plus 3 times 2 is 6 plus 4, that's 10. 5 times 2, that's also 10, right? So this equation is true, right? And then think about what would happen if you plug this on the left side and the right side. Okay, so instead of x, y, I'm setting u1 as this entire thing. So let's see what that gives us. First, what is u1 prime t? What's u1 prime of t? If you differentiate this,
5 over 2 e to the 5t.
This is not a fraction. This is just
Oh.
5 times 1, 2 e to the 5t. Is that right? Yeah. So because e to the 5t, if you differentiate, 5 comes to the front. And then think about what's 4, 2, 4, 3 times u1t is. Well, this is, no, 1, 2, sorry. 1, 2, 4, 3 times u1t is. This is 1, 2, 4, 3. And u1 is 1, 2, e to the 5t. And what is this? Right? What is this? 5, 1, 2, e to the 5t. So what do you see? This and this. Aren't they same? They're same, right? Okay, therefore you have the following identity. It's that because of this relation, we know that u1 prime of t is same as 1, 2, 3, 4 times u1 t. That's what I just showed. And the same thing can be done with this one. If you plug in the left side and the right side, on the right side, because of the because 1, -1 is an eigenvector, it's same, multiplying this to this is same as -1 times that, and that will be same as differentiating this. So this relation, I mean, the person who first thought about this must have been a genius, but actually it's kind of natural if you go deeper into the mathematics. There are some very nice thing called diagonalization of a matrix. And if you take that viewpoint, this is kind of natural. You really need the eigenvectors and eigenvalues. But for us, this is all we need to know. Okay, we're not going to go into diagonalization of matrices because that's too much. We're just going to say, oh, if you have the eigenvectors and eigenvalues, they're going to satisfy such equations. And because that they satisfy such a thing, if you write down eigenvector times e to the lambda t for the eigenvalue corresponding to the eigenvector, that will always become a solution. Okay? Now, if you know that that's the solution, then what is the general solution? These are two special solutions, right? What's the general solution? Add them together with C1 and C2, right? That's it. So the solution is that xy should be C1 times the first solution plus C2 times the second solution. That's the second solution. Now this is the general solution. And therefore, in order to make sure that it satisfies the initial condition, all you have to do is plug in t equal to 0 and then find out C1 and C2 that will satisfy it. Okay, so let's do that. If you set t equal to 0, what do you get? You get x evaluated as 0 and y evaluated as 0 equal to C1 times 1, 2 plus C2 times 1, negative 1. Where did the e go? Because e to the 0th power is 1, so they disappeared. Okay? Multiplying by 1 doesn't do anything. Okay? So that's what you have. And the top row says C1 plus C2 is what? It's the same as the top row here, which is
0.
X of 0 is what? 1. Okay? And the bottom row says C1, 2C1 minus C2 is Y0, which is 3. And you just have to solve this. Let's solve it by adding them. So 3C1 equals to 4. So C1 is 4/3. And plugging it back in here and subtracting, you get C2 equals to negative 1/3. So the final answer is that xy is 4/3 times 1, 2 e to the 5t plus negative 1/3 times 1, negative 1 e to the negative t. So that's a solution that satisfies. This is the solution that satisfies the original equation and the initial conditions. Now, one thing that you might be asked to do is to represent your answer not in a matrix form, but in terms of x and y. So you should be prepared to write this as x and y. So in other form, it's x of t. Can you read this, the top part only? What does it say? X of t is 4/3 times 1 times e to the 5t, right? Okay, and then minus 1/3 e to the negative t. And then y of t is
8/3 e to the 5t.
Then plus 1/3 e to the negative t. Okay? And you can actually verify that it satisfies these conditions, and you can even plug it in here to verify that it satisfies everything. That's how you solve a system of equations.